All right, today we're jumping into the world of chemical engineering education. It's the field that powers pretty much everything, from the medicine we take to the fuel in our cars. But is the way we're teaching it actually keeping up with how fast modern industry is changing? Let's get into it.
And that's really the big question we're tackling here. There's this growing feeling that a major disconnect is formed, between what students are grinding through in the classroom and what they actually need to know on day one of their careers.
So, what's at the heart of this problem? Well, while industries have made these massive shifts into brand new areas like biotech, a lot of university programs seem, kind of stuck in the past. Okay, now this slide really lays it all out. On the left, you've got the classic university focus, these huge, continuous petrochemical plants that just run and run at a steady state. The main goals there? Economics and how much you can produce. But then you look to the right, and that's what modern industry is wrestling with. Things like biotech, processes that run in batches, and designs that have to juggle a whole bunch of objectives like safety, environmental impact, and risk, not just the bottom line. And, this gap isn't just a theoretical problem. It has some very real and very expensive consequences. It means companies are having to spend their own time and money training new grads on skills that, you could argue, they should have picked up in school. So this is a practical and costly issue for everyone. Let's dig into a really specific example, the Senior Process Design course. Now, this is supposed to be the capstone experience for students, right? The grand finale. But often, it just doesn't prepare them for the messy, unpredictable reality of industrial projects. So, you know the drill for a typical project. You take all the theory you've learned, you design a plant on paper, and then you run the numbers. It's all about cost, sales, and return on investment. And look, that's a great exercise, but it's missing some absolutely crucial real-world pieces. Because in a real company, a design is never just about the money. Not even close. Engineers have to be asking, is this thing safe? Can we actually control it? What are the risks if something goes wrong? These are the questions that a simple ROI calculation just can't answer. And this right here is a perfect example of that disconnect. FMEA is a standard issue tool in the industry. It's how you systematically figure out what could go wrong with the design. It's straightforward, it's incredibly valuable, and yet, it's almost never taught to undergraduates. It's exactly the kind of practical skill that's falling through the cracks. Okay, let's pivot to another core area, separations. This is all about purifying products, but the way it's taught can be, surprisingly narrow. For decades, if you took a separations course, you were going to learn about two things, distillation and extraction. And don't get me wrong, they're super important, especially in the world of petrochemicals. But they're just two tools in a much, much bigger modern toolkit. And listen to this quote, because it really puts things in perspective. In the bioprocessing industry, which is absolutely booming, a totally different technique, chromatography, is often the real star of the show, and yet many students are graduating without more than a passing mention of it. So what exactly is chromatography? It's this incredibly powerful method for pulling pure components out of really complex mixtures. We're talking about the kind of high-tech process you need to make life-saving products like vaccines and insulin. So yeah, this is not some niche, obscure technique. It's right at the heart of modern manufacturing. All right, our last big area to tackle is process control, basically the brain of any chemical plant. And in this case, the source material suggests that academia is often working from a playbook that's, about 50 years out of date. And here we go again with this contrast. The textbooks are just full of theory for these perfect world systems. Continuous, linear, steady state. But the reality in a modern plant, especially a batch plant, is messy. It's nonlinear, it's not at a steady state, and it relies on all this discrete, time-based logic that the classic theory just doesn't cover very well.
So that really makes you wonder, right? If the textbook theory is so out of sync, what skills are companies actually looking for when they hire a new engineer?
Well, a survey of folks in the industry gives us a pretty clear answer. And just look at the top three: optimization, statistical data analysis, and process modeling. It is all about using data to make the process better, more efficient, and more reliable. And here is the real kicker. You know that classic topic that takes up so much time in a lot of courses, PID controller tuning? It came in at number 7 out of 10. I mean, it's still important, sure, but it is clearly not the top priority that university courses often make it out to be.
And if that wasn't enough, just look at these critical industry standards. These are literally the rule books that govern everything from how batch processes are controlled to how alarm systems are managed to prevent disasters. And yet, they're hardly ever mentioned in a typical university curriculum.
And let's be really clear here. These are not just some bureaucratic guidelines. They are the absolute bedrock of how you run a safe, efficient, and well-designed plant. Graduating without even being aware of them is a major handicap.
So, after seeing all these gaps, what's the solution? What's the path forward? Well, it's not about pointing fingers. It's about building bridges. This has to be a real collaborative effort.
This quote from the source material really just says it all. This has to be an ongoing conversation. Industry and academia need to be constantly talking, working together, not just to fix the problems we see today, but to actually anticipate the skills engineers are going to need 5, 10, even 20 years down the road.
And that kind of leaves us with this final, massive question. This isn't just about tweaking a few lectures here and there. It's about fundamentally rethinking how we prepare engineers for a world that is never, ever going to stop changing. So how do we build the curriculum that actually builds the future?